Tēnā koutou, tēnā koutou, kia ora koutou katoa, and welcome everybody to the Melting Ice and Rising Sea panel discussion. My name is Professor Grant Guilford. I'm Vice-Chancellor of Te Herenga Waka, Victoria University of Wellington, and it's my honour to welcome you all to this event. Tonight you'll be hearing from a group of 6 award-winning Wellington University researchers. These researchers are part of a wider team of 20 geologists, glaciologists, climate and social scientists from the University, GNS Science and the National Institute of Water and Atmospheric Research, known as the Melting Ice and Rising Seas team. They are behind the breakthrough discovery that Antarctica's ice sheets melted rapidly in the past and could have a significant impact on global sea level rise over the next 80 years, including causing sea level to rise by as much as 2 metres in some parts of New Zealand. Their work has involved annual expeditions to Antarctica over the past 15 years to collect ice and sediment samples that provide an understanding of how the frozen continent responded to past changes in the Earth's climate. They have used these insights from past warm climates to test and improve computer simulations of how the polar ice sheets melt and how they contribute to global sea level rise. With the evidence they have collected, the team is communicating with decision makers on how to avoid the worst impacts of modern climate change, including identifying limits for the melting of Antarctica and avoiding damaging global sea level rise through controlling human-produced greenhouse gas emissions. With this evidence, the team is also improving projections of sea level rise for New Zealand so that decision makers and the public are better prepared for managing and adapting to rising seas and their coastal impacts. For their work, the team recently received the prestigious Prime Minister's Science Prize. This prize is awarded every year for a transformative scientific discovery or achievement that has had significant economic, health, social or environmental impact on New Zealand or the wider world. The prize is worth $500,000, which in this case will support further work by the Melting Ice and Rising Seas team, including an enduring PhD scholarship for studying Antarctic ice sheet dynamics and the implications for sea level rise in New Zealand. Tonight you will hear these modern day explorers speak about the work that led to the Prime Minister's Science Prize, from fieldwork to scientific modelling to communicating their findings and working with local stakeholders to help New Zealand and the world manage and adapt to sea level rise. This work is a wonderful example of the multidisciplinary expertise we have here at the University and in our wider capital city. With this combined team of science, policy and communication experts, these researchers were able to take this work from fundamental discovery all the way through to science and policy ready to be applied to the modern world. Together, they have made a significant contribution to the university's role as a global civic university, and along the way, they have made us very, very proud. Tonight's discussion will be led by the indomitable Professor Tim Naish from the Antarctic Research Centre, team leader of the Melting Ice and Rising Seas team. Please now join me in welcoming the panel to the stage.
Well, ngā mihi nui, kia koutou katoa. Welcome everyone, and thanks Grant for that nice introduction. It's actually, I don't really need to say too much after that. You've made my job quite easy. Thanks Kylie and your team for organising this public event where we can share with you the research and some of the impacts that have come from that research that have won the Prime Minister's Science Prize. So as Grant said, I'm Tim Naish. I'm going to MC things tonight. I'm going to introduce you to the star-studded lineup here, which are members of the team, obviously. The team was a lot bigger. And in a moment, I'll tell you how we'll do things, and you'll have the opportunity to ask questions. So think of questions as we're speaking, and I'm sure we'll have a lively discussion at the end. But first I want to acknowledge the prize and sort of what it means to us. I mean, this has been a massive thrill and actually one of my worst kept secrets, and probably one of the one of our worst kept secrets, just because of the impacts of COVID-19, and you can see that it says 2019 Science Prize, and Andrew Clellan, the CEO of the Royal Society, rang me up in 2019 and said, well done, you've won this. And then of course COVID came in and we had to, things got delayed, and we eventually received the prize virtually in an online ceremony just very recently actually, so it's very new to us. We're still really excited. We're a little disappointed, and particularly our partners and families are disappointed because we didn't get to meet the Prime Minister in the actual ceremony. So I'm assured by the Royal Society we'll get invited to next year's awards, and that'll happen then. I'm not sure if Juliet Gerard is here. She was certainly on hey Juliet, you're up the back. She was on the invitation list, so it's great to have you here, at least Juliet. And yep, I've singled you out. Okay. And I also want to add that this is truly a team prize with a capital T. It represents many people's work over many years, actually, almost 40 years to build the foundations. And that's people like Fred Davey, Peter Barrett, Lionel Carter, and then with Peter and Alex Pine developing that pioneering drilling technology that's allowed us to make these discoveries in Antarctica. And, Peter couldn't be here tonight, unfortunately, but he's been talking about ice sheets collapsing, sea level rising, global warming for more than 40 years, well before it global climate change became a household sort of term. So we had to cut the team down for this from the 23 people, and what we've done is we've chosen a selection of the team to take you on a journey of that really spans spans what we do, from the very fundamental discovery-led, curiosity-driven side of things. You go to Antarctica and you discover cool things, to realising they actually have global significance, to then realising that there's this ongoing concern and growing concern about climate change and what's happening to the Antarctic ice sheet, and realising that your research has really important specific benefits and impacts for New Zealand. So as we go through the team, and each person talks, and in a moment I'll introduce each of them, I'll let them talk, and then when they've all spoken, you'll have been on a journey, on a storyline that takes you from fundamental discovery through to where the rubber hits the road and why this sort of research matters. I did want to also acknowledge that you can't do this sort of science on your own. No one institution can do it, and there's a lot of logos around from the institutions who did the science, and particularly want to comment and acknowledge the role of and the deep relationship we've had with GNS and NIWA over the years, and the collaboration that's ongoing with the Antarctic Science Platform National Modelling Hub and the Ice Core Research Facility. So those remain really important and deep collaborations which were part of this prize. And the sort of research we're doing from fundamental science all the way through to the applied end can't be funded out of any one program. And so that's why you see so many different organisations and funding agencies that have contributed to that funding. And I must acknowledge students. So our team of 23 are largely Antarctic Research Centre and the Centre for Science and Society, the Climate Change Research Institute, and then our national partners. But Students are the engine in this, so postgraduate students and graduate students have really been the engine room that's generated a lot of the science. Okay, so let's get underway. There we are. That's the full extent of us. And interestingly, just to point out, there are scientists in there, but there are also support staff, and it's the support staff, it's the clever engineers and technical people, and even people who just do the administration and the management that are possibly more important than the scientists. So, it's really great to see them acknowledged as well. Okay, so I'm now going to introduce our first speaker. They're each going to talk for about 6 or 7 minutes, and then so they'll come up here and then they'll sit back down again, and then we'll have the next speaker, and we'll save the questions until the end. So the first speaker is Rob McKay. He is the current director of the Antarctic Research Centre. Rob uses geological drill cores around Antarctica to understand how ice sheets respond in the past to climate change, and particularly warmer climates than we have today in the sort of world we're going into. Rob led the $20 million international ocean drilling expedition to the Ross Sea in 2018. He received the Prime Minister's Emerging Science Prize in 2010 for his PhD research, which I supervised. So Rob sort of holds it over me now. He has 2 Prime Minister's Science Prizes. So Rob will take us back to where it all began with some of those fundamental discoveries about what we learned about West Antarctica. Rob, take it away.
Thank you, Tim. So I'm going to keep it pretty simple in terms of how we go through these few slides and just ask a couple of really fundamental questions. And the first one being, when did that ice sheet last collapse? And the next one being how warm it was when that collapsed. And ultimately getting to the sea level question of how high was sea level. So there's certain things we can do with past climates and there's certain things we can't do. And so having to marry that up with people that work on human timescales, policy relevant timescales, is one of our challenges, and that's really where this group has excelled. And so within Victoria and Wellington in general, we have quite a large group of people working on the IPCC, the Intergovernmental Panel on Climate Change. And this picture here is a model projection under the worst case scenario in the last IPCC assessment report. So this is the concentration pathway 8.5. Which is extreme. It's looking at about a warming of just under 4 degrees Celsius globally by the end of the century. Important to remember that's operating over a 100-year timescale, and it's going to keep going. So that's actually a snapshot 100 years in the future, well, less than 100 years in the future. But the planet takes a long time to actually reach up with that forcing of increased greenhouse gases in the atmosphere. And on geological timescales, we can compare this to climates 3 million years ago. So we recently passed 400 parts per million CO2 in the atmosphere, and this is what it looks like when the planet catches up with that level of CO2 in the atmosphere. And you can see it's actually moderately cooler than what we saw in that previous projection in 100 years' time, or 2100. So here we're looking at about 2 to 3 degrees globally warmer. So this is just exceeding the Paris targets. So 2 degree warmer climate, the background colours there is the model run, and the dots are the geological data. So you can see here, there's places where those dots, the colour scales are the same for temperature change. They match up pretty well, and there's places where they don't. The data actually appears to be a little bit warmer than some of these models. So another thing we look at is how well do these past climates compare with model performance, and it helps to refine those models. One feature we notice in these models is that the polar regions warm up more than the rest of the globe. They approximately double the rest of the globe. And so the question then becomes, okay, 2 degrees global warming, what's that happening in the waters offshore of Antarctica, and does that cause an ice sheet retreat? So when Tim and the ARC, people like Alex Pine, developed the Anduril project, the question was, when did that ice sheet last retreat? And we didn't know that answer. We thought it might have been stable for 14 million years. It might have been stable at 400 parts per million CO2. So this is what the ice sheet looks like today. You can see here big ice shelves. These act to protect the flow of ice into the ocean. They actually slow down the flow of ice. So you remove those ice shelves, the ice sheet behind it disappears, and particularly the parts, sorry, the animations are not working here. This here is a marine-based sector of the ice sheet. So this means the ice sheet's sitting on the Earth's surface below sea level. It's intimately connected to the oceans, and you don't need a lot of change in the amount of temperature in the oceans or the amount of heat being pushed next to that ice sheet to initiate a retreat. And as the retreat gets initiated, it goes into a deeper setting further inland that you go in West Antarctica. So this is what's known as marine ice sheet instability. Once that retreat off this little topographic high begins, it becomes runaway and it accelerates. And so the question is, here, West Antarctica, we've got about 3.5 metres of sea level that's susceptible to marine-based ice sheet instability, and in East Antarctica about just under 20 metres. So how much of that goes in this moderately warmer climate of 2 to 3 degrees Celsius? And so we do quite a simple thing, sedimentology it's a first order observation. Was there an ice sheet there? And we just look at what type of sediments we pulled out of the drill core. So we drilled through the Ross Ice Shelf with the hot water drill system, we lowered a pipe to the sea floor and we collected over 1 kilometre of sediment. And the further down you go, the further back in time you go, because the sediments stack up through time. And so we saw these natural ice age cycles, times when there were bigger ice sheets than today, carries gravel, sand, muds. Ice sheets don't care what they pick up, they're like a bulldozer. As that ice sheet retreats and you get an ice shelf, very weak ocean currents wash muds in, occasionally a pebble will fall out of that floating ice above the site, and you get these muds with gravel. And I actually have the core down here, just showing these colour changes. So you can just look at the colour changes. And when you get to the open water conditions above the drill site, what's recorded are plankton living in the ocean surface will settle to the sea floor and form what's called a diatom ooze. So these are shells of marine plankton, indicating there are open waters above the site. So we mapped the core, we mapped where these sediments occur in the core, and we compare it to, at the time, quite revolutionary ice sheet models that could first capture this relationship between ice shelf collapse and the loss of that grounded ice sheet behind it, the ice that contributes to sea level rise. So we'll colour code it there, the yellows being open water conditions above the drill site. Oh, okay, Microsoft fail. So the yellows doesn't really matter too much here, the gobbledygook. This is 3.5 million years ago, this is 2 million years ago. And so you can see that you've got this time sequence getting into this sweet spot of the Pliocene time period, 2 to 3 degrees warmer. We were seeing fossil species that today live north of the polar front. They live in waters that are completely intolerant of sea ice. So we had 3 to 4 degrees warmer temperatures in the Ross Sea during those peak Pliocene warm periods. So 400 parts per million, it matches that relationship of double the warming in the polar regions compared to the global average. But even in the more recent record, up to 1 million years ago, we're still seeing these collapse events. And this is occurring when there is sea ice in the Ross Sea, fossil species that are about 1 to 2 degrees warmer waters. We could look at chemical compounds and also trace some chemical tracings for those temperatures that came out at those same temperatures. So it doesn't take a lot of oceanic warming to initiate that loss of those ice shelves, and with it the ice sheet behind it. So that was almost 10 years ago. We did the Andrel project and we came up with these numbers. The models were catching up with us at that point. They couldn't lose this amount of ice without having to put extra physics into their models. And so what we are at now is looking towards the East Antarctic ice sheet. So after Andrel, I was involved in an IODP expedition off the coast of Wilkesland here, and this is a model run by Nick Golledge for the Pliocene, where he was using this geological data to constrain how much ice loss he would be able to tune in his models, to get out of his models. And in these Pliocene climates, we're looking at sea levels exceeding 10 metres above the present day, potentially up to 20 metres from some other geological archives around the world, including in New Zealand. We've recently cored in the Wanganui Basin, showing that East Antarctica was highly sensitive to these warmer climates, potentially large parts of that larger East Antarctic ice sheet. So that's where we're heading to in the future. We're looking towards that sleeping giant of the ice sheet that we thought 10 years ago, before Andrel, was stable and pretty insensitive to change. What we can't get to with these geological records, so I've got to magnitude, we've got to how warm it was, we can talk about magnitude of temperature, magnitude of ice loss, but we are dealing with timescales of thousands of years in these geological archives. How do we get to what is relevant in 100-year timescales? And so that's where we're going to look at some of the more recent ice age cycles, and then also how we can use models to inform on that rates of change, because that's the key thing that's policy relevant. Thank you.
Yeah. Okay. Oh. Yep. Give it a clap. Rob, I apologise, I did not booby-trap your slide. It was perfect on my screen, so I don't quite know what happened. But scary stuff, right? 400 ppm, the concentration of carbon dioxide we've got in the atmosphere now. the West Antarctic ice sheet goes away and some of the East Antarctic ice sheet. That was the first time we got quite concerned. Okay, so it gives me great pleasure to introduce our next speaker, which is Nancy Burtler. And Nancy holds at least 3 jobs I'm aware of, and there could be others. She is director of the Antarctic Science Platform, hosted by Antarctica New Zealand. She is associate professor in the Antarctic Research Centre, and she runs the New Zealand Ice Core Research Facility, where she is a principal scientist at GNS Science. Nancy was awarded the Blake Leadership Medal, I think in 2017, or my memory might be fading me, and this was for her outstanding development and leadership of ice core research in New Zealand. Tonight she will show us what ice cores can tell us about global warming and how fast sea levels can rise. Nancy.
Yeah, thank you very much. As Rob just mentioned, we look at the geological records to find out how much sea level we anticipate when the climate stabilizes. But the other key question is really how quickly we see sea level rates change on timescales that matter to us and policymakers. And this is where the complementary work between these deep marine sediment records and other archives with ice core records provide us some real unique opportunities. So one of the studies that we can use, and that might seem a little bit odd to you, is actually looking at the last ice age and just looking at, from the last ice age, how quickly these ice sheets lost mass and sea level increased as consequence of that. So during the ice ages, global temperatures was about 6 degrees colder. And as these ice sheets melted, coming to today's conditions, sea levels rose by 120 meters. Of course, a lot of these ice sheets are gone now, so we're not expecting quite as much to remain to melt. But this is an area where we can really look at rates, how quickly can the ice sheets change. So in front of you is a very boring graph that shows the last 22,000 years. And I'm just showing you now how from the last ice age to today, sea level changed. So we're starting off below 0, and 0 is today's sea level. So here's the last ice age. We still had mammoths roaming the northern hemispheres, and then it got warmer. So here's the sea level rise. And I can talk for hours about this very simple graph to undergraduate classes, but here we keep it short. And one of the really key things is that for the last 10,000 years in our graph, sea level didn't change very much. Right? We as societies are really used to very stable conditions. Another really interesting part of that is if you think that over this time period we increased sea level by 120 meters, that makes about 1 meter per 100 years, so it's quite fast. But of course we had these large ice sheets that melted away. But then it's not a linear graph. We have these odd blips in there. And scientists aren't very creative people. We need other folks to help us with that. We call these things meltwater pulse 1A. Couldn't come up with something better. But during this meltwater pulse 1A, rates change for 500 years to 4 meters of sea level rise every 100 years. And if there's policymakers in the audience, that should really scare the heck out of you, because that would be a massive, massive challenge. For a long time, we didn't think that was policy relevant because we thought it would come from the northern hemispheric ice sheets that no longer exists. But then Nick Golledge, about 4 or 5 years ago, and also a group in Germany independently, identified this melt pulse as actually having a very large contribution from Antarctica. And that made us sit up, because suddenly Antarctica is still here. This is suddenly policy relevant. If we can have faster rates, we need to know about them. So this is where ice cores can be very, very useful. Ice cores, a little bit like tree rings, can collect very nicely continuous records over time, and that allows us to look at fast things that happen over just a few years. You see this beautiful image there from a snow pit, and about 20 centimeter chunks of those are annual layers. So we can drill back in time hundreds of thousands of years, and for the last tens of thousands of years, we will actually have seasonal resolution. We can look at summers 12,000 years ago. But also, ice cores have this really nice ability, as the snow compresses under the weight of the new snow, it slowly forms ice. And when it forms ice, it creates bubbles. And at that time, it captures greenhouse gases. It captures all gases, but also the greenhouse gases. And so while ice cores can tell us a lot about temperature of the globe. It can tell us from the chemistry what the oceans and other aspects of the Earth system have done. It also can give us a direct record of past greenhouse gases. I also just wanted to show you a picture of the last ice core program that we ran out of New Zealand. It was a 9-nation project. We were very proud to do this, but the only reason we could do this was because of our engineering team. This is a drill. There's only 2 such drills that exist in the world. And our engineering team, for them, that was just a side project because normally they are dealing with even more complicated drilling in the oceans. But they not only modified this drill to have additional capability and deliver us this beautiful drill ice core, but also the engineering that went into the National Ice Core Facility at GNS allowed us to do things that weren't possible elsewhere before then. And so it's really the engineering that is one of our secret sort of weapons that allows us to do things that gives us a real advantage, and so it allows us to develop new technology to support our science. But then what did these records tell us? This is a most iconic record from Vostok, which shows us the last 400,000 years. At the bottom, you see 400,000 years where we get the temperature from the ice core record, and then from these tiny bubbles we can extract CO2 and methane data. And as you can maybe see, we go through these warm periods and slowly cool into an ice age, and then we go into a warm period and go back into an ice age. And we do this about 4 times in the last 400,000 years. If you compare the temperature with the greenhouse gases, you can sort of see for all intents and purposes that they look the same, which really was the sort of first indication that greenhouse gases drive global temperature at a very sensitive rate. But to zoom in now into today's time, we go from 0 to 2000, and the time frame changes. So now we just look at hundreds of years. And none of that will be news to you. We have the huge increase in greenhouse gases with a smaller increase in temperature. And we, of course, were interested why the increase in temperature didn't match the temperature increase in the past. And we know now that 93% of the heat produced by the greenhouse gases that are now in the atmosphere are absorbed by the ocean, which slowed down the atmospheric temperature. I'm going to show you a really busy graph, and it's the last graph right now. But I only want to show you why we actually now have to hand over to the modeling community. So this is the records from Antarctica and Greenland. They're color-coded. Greenland is purple. Then we have beautiful records from East Antarctica in green, some from the Ross Sea in blue, and West Antarctica in red. And what I want you to take away from this is that there's very abrupt changes. We see huge climatic swings about that have started in less than 5 years and then sometimes lasted for 500 years. So we know the climate system is really capable of very, very fast changes. But to make sense of this wiggly mess, we actually need help, and we need help with models that put that into perspective of a representation around the entire globe rather than single spots, and also to test processes and thresholds. And so this is where really the collaboration with the next speaker is helping us to make sense of those data, as well as allowing us to verify the quality of the records by trying to reconstruct what we see in the data. Thank you.
Great, thank you, Nancy. So now we know ice sheets are pretty sensitive and go away, and they can go away really quickly, and sea level can rise really fast, like 4 metres per century. But how fast can Antarctica melt? I think we're about to find out. So within a team of very impressive scientists, Nick Golledge stands out. His head is big enough, as you can see up there. So I won't say any more. He is associate professor, I will say some more. He is associate professor in the Antarctic Research Centre and leader of the Antarctic Science Platform National Modelling Hub. He is also a leader in he's a lead author on the IPCC's current assessment report. He is a numerical ice sheet modeller, and his research group is really leading the world with their modelling of understanding the Antarctic ice sheet, how it melts and how it contributes to sea level rise. He has this incredible record I'm going to embarrass him with. He has published 6 papers in the world's most prestigious scientific journal, Nature, in the last 6 years. That's 1 a year, so no pressure, Nick. The next one can't be too far away. All right. So I better let you do some talking, eh? So I'll hand over to Nick.
Okay, thanks, Tim. No pressure. Okay, let's get into the science. Okay, so I run computer simulations, basically. So I try and understand how the ice sheet behaves by having a very small representation of it on my computer screen, and then I try and disturb it, try and upset it and see what it does. But one of the important things about any kind of modelling process is having some constraint for those experiments. And the kind of work that Nancy and Rob have described in the last two talks is really fundamental. So getting those geological records, getting the ice core records, those are the things that tell us how the environment has changed and how the ice sheet has changed in the past. And that's what we use as our targets when we're running these simulations of the past. So what I'm showing here on this graph is on the top panel there in the green colour, that's a sediment record, the kind of thing that Rob would get from the sediment cores that he's drilling. This is actually from the German group that Nancy mentioned. But the reason I'm showing it is because they drilled this sediment core from the Weddell Sea. We tend to work in the Ross Sea. They recovered this record, and basically the height of the bars there tells you some indication of the relative magnitude of change of the ice sheets during that last deglacial period that Nancy mentioned. So basically what we can see is these rapid changes. This is spanning 10,000 years there. But you can see that the ice sheet isn't just losing mass smoothly. It's what Nancy's talked about. There are these abrupt meltwater pulses, times when the ice sheet responds very, very quickly, and we lose a lot of that ice into the ocean. Now, we were running computer models constrained by different data at this time, and as it turned out, we managed to get an amazingly good fit to that sediment record. And the reason that we got that fit was because we'd managed to incorporate into the model the processes that allow the ice sheet to behave dynamically. And this gives us a really good first order check that the models are doing the right kind of thing. You can kind of think about it like like shooting a soccer ball through goalposts. If you've got one goalpost in front of you, it's pretty easy to kick a ball through that. But if you've got a whole stack of those goalposts, one behind another, and they're all slightly different sizes, you've got to get things just right to go right through the middle. So that's kind of what we're doing with these constraints that we use on the models. Now, the reason that we do that, of course, is we want to use these models. We want a bit of basically trust the models when we do the future projections. So what we're trying to do is get those models behaving correctly, or what we think is correctly based on the paleo data, the geological records. And then we say, right, we've got the physics that we need, we've got the behaviour that looks like what we've seen in the past. Let's just change the climate forcing we put in there. We'll put in a future forcing, some of the RCP scenarios that we've heard about, and see what the ice sheet does. Now, the curious thing about ice sheets is that we've got a real timescale issue. When we look at the response of an ice sheet over maybe a year to a decade, it doesn't really do a whole lot, to be honest. It melts a small amount. When you warm the air or you warm the ocean, it melts a small amount. But what really, really matters is what happens after that. So when we start looking at decades to centuries, that's when we start to see what we call the dynamic response. And this is what Rob was talking about earlier, that marine ice sheet instability. We start seeing thinning and acceleration of the ice sheet as it flows into the ocean. Now, the key thing here is that if we've got our model tuned correctly, we can tell when that dynamic contribution will kick in and the kind of the environmental conditions under which those changes might take place. And it turns out that when we run these experiments with different levels of climatic forcing, we can see that there's a separation in that trajectory of change, and it seems to be around about the 2 to 3 degree mark. So kind of critical, and that's sort of above sort of early industrial levels. So pretty much around the Paris Agreement kind of limit. Now, of course, when we go beyond that time frame, we're seeing that ongoing loss. And this is something we think about in terms of the commitment. This is something that the change is going to happen way beyond our lifetimes, probably beyond the lifetimes of our children, maybe even our grandchildren. But we're setting in place changes now that will play out over hundreds and thousands of years. It's very, very hard to stop that ice sheet going once it's gone. So actually, finding out right now which line we're going to follow is pretty important, and we can pretty much narrow it down to staying below about 2 degrees, so that in 1,000 years' time we've only lost a small amount of the ice sheet rather than something like 10 meters. Now, of course, one model is never going to be reliable. We can always find problems with anything that we look at. So a large part of what we do in this group is we contribute to these big international collaborations. The projects where we're bringing together ice sheet modelers from all over the world using very different models, using different approaches, even if they're using the same model. And the idea here is that the more we pull these models together from different groups, the more we can see where they're similar and where they're different. And the key thing about Antarctica, as you can see there on the left-hand side, Greenland is that sort of quite narrow green-coloured spike. Basically, the behaviour of Greenland's quite well understood. It tends to melt as the air gets warmer, but it doesn't respond too much to the ocean. Antarctica's the wild card. It's a much bigger spread there. That blue polygon, whatever it is, bell. And that's because of this dynamic contribution that we don't really fully capture or we don't really understand in the models too well. So there's still a lot of work to do there, and that's why we need these intercomparisons. But the thing that's clear is that basically if we follow a high emissions scenario, we will see much higher mass loss from Antarctica. If we follow a mitigated scenario, we'll see much less mass loss. Now, the key message to take away from these intercomparisons is that people sort of tend to focus on the range that you get and say, well, the models disagree, there's uncertainty. But you've got to remember that for every model member you add to that ensemble, the stronger your central tendency becomes. So that median line in the dark colour becomes more certain with every model you add. So even if the uncertainty increases, you're more sure about the middle. And that's a key thing when it comes to deciding on policy decisions. And I'll leave it there. Thank you.
Great, thanks very much, Nick. And that really was a massive discovery, I think, I know that Nick was the first to really identify that 2 degrees could be a tipping point for the Antarctic ice sheet system. Okay, whose turn is it now? Richard Levy. It now gives me great pleasure to introduce Richard. Richard is the research leader of the climate and environment theme at GNS Science, where he too is a principal scientist. He is also an associate professor in the Antarctic Research Centre. He developed and currently leads the New Zealand Sea Rise Program, which is improving location-specific projections of sea level rise, and he will be talking about that tonight. Richard is one of these remarkable people. He's a jack of all trades, a master of many, and his skill set spans paleoclimate science, sea level projections and impacts, science communication and engagement. So Richard will explain to us how we predict sea level rise using these models that Nick has talked about and what that means for New Zealand.
Yes. Good evening all. I just want to point out that Nick Golledge has no numbers on those graphs, which is interesting. I'll try to put some numbers on at least one or two I show. Yeah, so my job here tonight, I guess, is to bring a lot of the discussion, the science, the discovery that you've heard about around Antarctica closer to home, to the coastal regions of Aotearoa, which is an area that many of us are concerned about and interested in. So I'm going to talk a little bit about some of the work we've been doing in the New Zealand Sea Rise program. It involves many people on the Science Prize winning team, but also many others that I'll acknowledge some of as we go through. Now, we've talked a lot about ice sheets and their contribution to sea level rise, but of course there are many other things that are contributing to our oceans' growth in height, including thermospheric effects, the expansion of the oceans as they warm up, the melt of glaciers and ice caps, and there was a nice, well maybe not a nice paper, but a concerning paper attributing some of the glacial melt in the South Island of New Zealand that came out in a paper today, got some press today or yesterday, so I'd encourage you to check out those news reads documenting how our own glaciers here at home are retreating. Ocean dynamics play a role in causing sea level to go up or down. Depending on where the heat in the oceans flow causes the ocean's height to rise more or less. Land water storage. Aucklanders know much about the issues around land water storage given recent stresses they've undergone, but the amount of water humans take and put on land, or the rainfall on the land gets captured in the soil, actually keeps water out of the ocean, and of course if you release that water back into the ocean, oceans can go up. And then land movement has an effect on local sea level, what the sea level will actually do around our coastlines. And so when we're trying to understand and project sea level, we've got to consider all of those components. And when I say we, I don't mean any of us sitting up here, because we don't know how to do this. But we are working with two of the world's experts, if not the world's experts, at Rutgers University, who take all of this information, all of the information from models that project into the future what will happen to land water storage, ice sheet melt models such as Nick's been talking about, glacier melt, put it all together into a probabilistic framework to actually produce a local sea level projection. And that's what the New Zealand Sea Rise program is attempting to do for us. We're going to be projecting all around the coast of New Zealand, all around at about a 1 degree spacing to produce location-specific sea level projections. And this will really enhance what has been done up to this point through New Zealand's coastal hazards guidance, which has taken all of the information that is available and given a sort of nationwide projection for our coastlines. We're trying to get to a little bit more detail than that to tell you what sea level will be what sea level will do in the Hauraki versus in Dunedin versus on the west coast, so that decisions can be made with the most relevant information. I'm just going to talk a little bit about one of the challenges we have in making these projections, and this is one thing that in the coastal hazards guidance was acknowledged, that vertical land movement wasn't included in those projections for New Zealand. And I suspect most of us realise that our land is quite dynamic, goes up and down. We feel earthquakes fairly regularly. But what I'm showing here is some plots from our GPS stations. So we actually measure in New Zealand our vertical land movement, or our land movement through GeoNet, which obviously is looking at horizontal displacements as earthquakes occur, but also vertical offsets. And what these graphs here are showing, these brightly coloured graphs, is several stations from Auckland all the way down to Dunedin, some GPS stations showing the relative motion of the land across annual timescales. And just drawing your attention to Wellington here, there's a gradual decrease, a slight rise when a major earthquake occurs, and so on and so forth. So you're seeing that over time this land is going down. And of course, if land is going down and sea level is going up, then that amplifies or extends the amount of sea level that you'll get on the coastline at that point. If the opposite is happening, land's going up, sea level's going up. If the land rate rises faster than sea level, then you'll actually not get a local sea level rise. So it's really important to get this component as accurate as possible. We're also using satellite interferometry. This is a colleague of mine at GNS, Ian Hamling, is using essentially a satellite that's orbiting the Earth, beams down a radar, bounces off the Earth back to the radar, and you can actually measure at sub-millimetre resolution changes in elevation as those satellites orbit. Pretty amazing stuff. This is an image or a compilation of some of the data from one of those satellite-derived vertical land movement measurements. And you can see the whole of New Zealand in this plot here. The blues are areas that are going down, and up to 8 millimetres per year in some of these coast places. So this part of the east coast of the North Island going down quite rapidly. An area here, Pikawai, along the Bay of Plenty, going up fairly rapidly. So you can start to see we can get a broad nationwide coverage of vertical land movement that we can then integrate into these sea level projections. This is a close-up of Dunedin, just showing you how regionally you can get quite a lot of variability. This is reclaimed land, and it's going down around 5 millimetres per year. Bunnings Warehouse has got a big crack in it, apparently, from where the land's settling. So sea level rise along this coast will be much more rapid than sea level rise along this coast. So you can see how the spatial variability it's important to get sorted. This is just an example of how vertical land movement can make a major impact on your sea level projections. This is a plot that we've generated from the data that Bob Kopp and his colleague at Rutgers have produced for us. So this blue line is actually a modified sea level rise or sea level projection for Dunedin using this location, so offshore Dunedin, showing under a relatively high or warm climate scenario. It's not RCP 8.5, but it's a high-end climate scenario, showing what sea level will do out to 2100. So 1 metre, just over a metre of sea level rise in the Dunedin area. This is the actual tide gauge measurement produced from our colleagues at NIWA, showing that we're tracking along that path. But of course, we're not going to know really how we end up until 2030, 2040. But this is the effect that a vertical land subsidence of 5 millimetres. So in that harbourside area, this is what the vertical land movement will do to that sea level projection. And from a policy point of view, essentially the take-home message is it brings everything forward by about 10 years, a decade. So if you're planning on a certain magnitude of sea level rise by 2050, you add in vertical land movement, you've got to bring your thinking forward by about a decade. So vertical land movement matters in New Zealand. Of course, the opposite can happen where regions are going up. What we're starting to do now in the Sea Rise program is take some of these new projections and start to look at physical impact studies. And this is just one example showing what we're doing with Otago Regional Council and Dunedin City Council, taking a groundwater model for the South Dunedin region, and this is a model that's been run 100 times over and over again under modern conditions, just to see what model variability, to capture the range of model variability, showing which regions are likely to get groundwater inundation in a probability landscape. So relatively high probability of flooding in this area today. If you start to use some of those higher end sea level projections, this is what the probability looks like by 2100 under RCP 8.5. So you can start to see how sea level rise affects the probability of inundation in the South Dunedin region, and this is the difference between today and 2100 under those high sea level projections. So these are the sorts of things where you can start to look at flood frequency, start to bring in the physical system science into a risk-scape analysis, to then start to inform policy around when you may need to either increase your storm water system efficiency or perhaps enter into some kind of managed retreat. So this is bringing the physical science and trying to put it into a planning perspective, and I think we're going to hear a little bit more about that from the next speaker. So thanks very much.
Yeah, thanks, Richard. And you did right. We're about to hear a little bit more about the implications of those sea level rises for New Zealand. So, I mean, the picture that's evolving is not only did we underestimate the potential contribution of the Antarctic ice sheet to sea level rise for New Zealand, but we haven't yet taken into account those vertical land movements, which obviously make a big difference. So Judy Lawrence, our next speaker, is well known to many of you. She has many years' experience of climate adaptation and mitigation policy and recently chaired a ministerial climate adaptation task group. She has worked across government for many years before doing a PhD in sea level rise adaptation and decision making at the Climate Change Research Centre at Victoria University of Wellington, where she holds a part-time senior research fellowship. It's just as well it's only part-time because Judy is also a newly minted commissioner for the New Zealand Climate Commission. She is a coordinating lead author. That means she's in charge of a chapter for the IPCC report, and it happens to be the Australasia chapter. And Judy's work is at the very applied end of our team. And we like to say where the rubber hits the road and where the science evidence meets decision making and policy development. So, Judy.
Good, thank you, Tim. Well, if you thought that was hard, actually doing something about it is the most challenging thing we have to do. And I think, in summary, this 2 degrees we have to keep to. And the only way we can do that is to reduce our emissions. But unfortunately, we have quite a lot in the pipeline still coming, which is the lag that Nick talked about earlier. And so that lag is what we have to adapt to. And that is a difficult task, but which has been a team effort across many organisations. And I have to take my hat off to my colleague Rob Bell, whose picture's there, and the NIWA people, because we've forged a very good relationship in actually taking the science and working with the people who matter, which are our citizens. Now, what we need to do to address this problem of adaptation is that we need decision tools, we need to be monitoring what we're doing, and we need to have what we call enablers. In other words, the instruments that are necessary for decision making. And what this is actually what has happened as a result of all this work we've been doing is that across Victoria University we interact with our lawyers, we interact with our psychologists, we interact with a whole number of people, our economists, and we have a very tidy team. But we can't do that without our international colleagues as well. And I'll come to that in a minute, because we work with the Dutch very closely. Now, why do we need to have particular tools for adaptation to sea level rise? And I think you might have a hint of it in the earlier talks. And this is because in the near term, we're fairly certain about what is going to happen, because it's sort of happening now and it's developing. And we're getting a better understanding of what the rate of that change is from the work that we've had presented tonight. However, around that 2040 period, which both Richard and Nick have talked about, things start to diverge and the uncertainty increases. And it's what we call deep uncertainty, because we can project things, but they're not predictions. We can't know in the future. And so we need tools that can deal with that sort of uncertainty. And enter the Dutch on the left-hand side. One of my colleagues, Marjolein Hashnuk, has developed this idea of a metro map to think about the problem over time as the sea level rises. It is changing over time, but we don't know exactly the rate and we don't know exactly the timing of this 2 degrees. We've got an idea, but we don't know exactly within the time frames that we make decisions. And so if you can think of going to the London Metro, it will be a while, but if we think about that metro map, we can get to a destination through a number of means, different routes. And we can visualise those and think about the conditions under which we are going forward. And if we take an action, we ask these questions along the bottom, which are under what conditions will the strategies we're doing now fail? And so we actually use scenarios to think about that, what the future might look like that would actually condition something to fail, like a stop bank, like a levee, like a seawall, and the like. It could be a human failure, because it could be a coping failure, which could actually be much sooner than the actual failure of a levee, for example. And so along the bottom of this metro map, we use scenarios to do the what-if exercise, to say, if we did this, and this, and this, what would it look like in the future? Where are the conditions where those options would fail? And so we develop a set of pathways. Now, we've used these already in New Zealand. They were first applied in the Hutt Valley. It was a first for New Zealand, and actually a first probably in the world, because it was a real-life decision that was being made about the completion of the Hutt River flood management plan. We've now applied this in Hawke's Bay for the coastal area, and we're about to develop further the work to indicate signals and triggers that might develop and where these points are where we need to make decisions in the future. And the picture in the middle is one of Scott Stevens from NIWA, who put together some coastal pathways to visualise with the Hawke's Bay people what it might look like in the future. Now, as well as the climate scenarios that we've heard about tonight, we've also developed in another program shared socio-economic scenarios. So we can think about what sort of world we might be in the future, whether it's a kicking and streaming, 100% smart and unspecific Pacific, etc. And we describe these, they're narratives, and we test these against the options that we're developing for coastal management. And so we ask, as well as under what conditions will the strategies fail, how sensitive are the options to each of those scenarios and what alternative paths can be taken? And most importantly, can we change path? So we ask that question about path dependency as we go through this process. There's no point in building something that has a long lifetime but which you can't actually change along the way as the world changes around you. So that's working with uncertainty and change. And also, the work that we've been doing has been integrated into the government's coastal hazards and climate change guidance, and this is a very simple 10-step decision cycle that was developed. Rob Bell led this process. I was a co-author, and there were several others involved, including Sylvia Allen, who's a planner. So again, we're working in very good disciplinary teams, and we ask what is happening, what matters most to communities, what can we do about it, how can we implement a strategy, and how is it working or we're monitoring. Because we want to iterate through a process as the world changes. So we need something quite dynamic. And we've developed indicators. I mentioned them a minute ago. These indicators aren't just when the water's lapping up in front of us. They could be cultural indicators like the loss of taonga, and we've already seen some of that happening in New Zealand at the coast. They could be social indicators. How many times in Auckland going to Mission Bay do people going to work want to be disrupted, for example? What's the coping level of that community? And environmental indicators like the loss of amenity, and we already have insurance indicators. We have a signal already that the insurance industry is making adjustments to both their price or the pricing of risk effectively. And that will come through in premiums and also lack of cover or removal of cover. Increasingly coastal areas are not covered for inundation flooding, coastal flooding. And so the way we think about this is to have these signals or warnings, and we want to be able to trigger a decision well before we meet these coping thresholds. So this notion of lead time again comes in here, because it takes a very long time to get up at some sort of protection work. You can throw a truck of rock over a beach. It will probably only last a few years, and if you build anything stronger, there's still going to be a residual risk when these numbers keep coming up. And we've developed a routine, if you like, for decision makers to think about how they go about monitoring the system, and that's the picture on the right. So lastly, what do we need to have to be able to do this adaptation work, as well as the science that we've heard about tonight? We have to understand not just the hazard, but we need to understand the risk, and that comes down to what is at risk. NIWA recently completed an excellent piece of work looking at where all the coastal risk areas were, and most of the problems occur well below 1 metre of sea level rise. And just by way of example, in Petone, you only need 30 centimetres of sea level rise before you have to completely change your drainage system from a gravity drainage system to a pump vacuum system, or something else. And we have students who've been working on this problem, which is starting to inform how you might manage the retreat of coastal areas. And I have to say there's a lot of interest. We've just posted a paper out a couple of weeks ago, and there's been lots of email traffic interested in this sort of work, because nowhere else is actually doing it in quite the way we are here. We need to be communicating the risk. We need to have the statutory mandates sorted, which they're a bit of a mess at the moment, and there was a 531-page report came out last week by Judge Randerson, and he has an excellent plan. So now we need that plan to be implemented, where the mandates, the guidance and the codes of practice can be developed in New Zealand. But the elephant in the room is really funding and compensation and issues like that. When you're dealing with existing uses of land, proprietary rights, etc. And the Randerson report also addresses that issue and suggests a Managed Retreat and Adaptation Act where a fund might be set up, which is pre-funded like a superannuation in a very similar way and can help. So we need to get prepared, and it's urgent. Thank you.
Yes, thank you, Judy. Very, very wise words. Our next speaker would have been Rebecca Priestley, and there she is, but her husband has a book launch tonight, and so that sort of took precedence, which we completely understand. But I just want to talk a little bit about the last aspect of the team, which is Rebecca and science communication. So Rebecca is an Associate Professor and Director of the Centre of Science and Society at Victoria. She is a public engagement expert whose research spans the history of science, earth science and science communication. She's written a lot of books you're probably aware of. She's a great science communicator, and she's particularly concerned in how we get our message across and are we getting it across correctly. And so she ran this survey, and the results are really interesting. I'm just going to show you a couple of them, and it was to gauge the public understanding of what's happening with sea level rise. How much do you expect? But before I show you the survey, I'm going to ask you a question. And this is the start of the audience engagement, and then we'll throw it open to general questions. So, hands up if you think sea level rise by the end of the century around New Zealand, on average, will be greater than a metre. There's no right or wrong here, guys. It's not a... Yep, okay. Those are the pessimists. And hands up those who think sea level will be less than a metre. Yeah, okay. Interesting. All right, let's try... It was about 50-50, by the way. So let's try another question. What do you think is the worst case scientifically plausible sea level rise we could expect by, I'll give you a hands up in a minute, by the end of the century? Is it above 2 metres? Who thinks it could be we could get more than 2 metres of sea level rise? Yes, that's interesting. Who thinks we could get more than 3 metres of sea level rise? And this is if Antarctica does bad things and the land suddenly drops. Well, let's leave that out of it, but if we get some vertical land movement, yeah. Okay, there's a few of you. Okay, let's just quickly look at the results of Rebecca's survey. So the first one at the top is asking people, how much do you think global sea level is projected to rise? And I guess you reflected that the results of that survey. 50% said less than a metre and 50% said more than a metre. And in this case, 8% said more than 5 metres. Right? And then below, you can see that there are a substantial amount of people that are, there's some pretty biblical things about to happen. There's sea level rise of more than 15 metres. So this is a concern that we're not getting our message across. This is worst case scenario, but so the scientifically plausible worst case scenario, you wouldn't expect more than 2 metres of sea level rise by the end of the century, I think would be safe to say. And so why aren't we getting our message across? Is it because media are tending to go towards the more dramatic stories, the higher numbers? Is it because perhaps scientists are doing that as well? Is it because, the uncertainty? There's so much uncertainty as we've seen in sea level rise. So we'll just leave it at that, there in terms of the communication, but it's really important that the things we are finding out and discovering are being communicated correctly, not only to the public, but also engagement with stakeholders who need that information. We'll leave it at that. So thank you very much for coming along. Hope it's not too depressing and you go home and, maybe you need a glass of wine, but thanks very much. And,